Alright, welcome to our first screencast on the topic of electric current. So we're going to use the concepts of static electricity to start moving the electrons, which we'll call our electric current, from point to point and get them to do work. So first we need to kind of think again about what work is and energy and how we can apply that to an electrical system. A word of caution, we have talked about how it's the negative charges that move, it's the electrons that move. So we're going to stick with the idea that it's the electrons, the negative charge, that is moving. PhysicsClassroom.com uses the idea of a positive charge, known as conventional current. It's going to make everything about the motion backwards, everything about the potential and the potential difference backwards from how I will explain it, trying to stick with the actual current. If you do, I did not put any of the links for Physics Classroom on here because of that, but if you do go look at their website, make sure that you keep in mind that every time they show a charge like here, they'll be showing it positive, not negative, and therefore it would move against the field, not with the field. Okay, so we're back to our ideas of energy, and then we're going to try to tie that in with our electric field. The electric field itself is defined as the direction that a positive test charge would be accelerated. So if you look at our picture here, these lines represent the electric field. A positive charge would be moved in that direction with the field. Now, a negative charge is always going to want to move against the field. It's going to want to go from the negative, which is going to be up here, to the positive. So they're going to move in opposite directions. Turns out it's very similar or analogous to what we do with gravity in terms of energy. So we'll revisit potential energy in terms of changing our position inside the circuit. Okay, so a quick reminder: gravitational potential energy. If we have an object here on the Earth, the ground would be our 0 point in terms of potential energy, and if we have something from a higher point that falls, then it's going to give up its potential energy and turn it into something else. In this case, motion, kinetic energy. So it'll speed up as it falls. In that particular point, if gravity is the only force doing the work, then there are no non-conservative forces, and then the highest potential would be furthest from the place where it's going to want to fall, and therefore it would be at A. In fact, by the time it reaches the ground, it would have zero potential, or zero potential energy left. Now, if we have something at a lower point, like the ground, and we want to get it to a higher point, then we actually have to apply a force that is non-conservative, an external force, and that means we're going to increase the potential energy. It's going to be very similar within an electrical circuit. We're going to use batteries and power supplies to increase the potential of an electron, and then we're going to send it around a circuit, and as it moves, it's going to use that potential that we gave it to make things turn on, lights, move motors, whatever it is we're trying to get done. Okay, so in our case, again, the thing that's moving is not going to be a rock, it's going to be negative charge. Whenever we are going to need to do work on the negative charge, it's when we're going to be forcing it to move to the place it does not want to go. And negative charges do not want to go near negative charges. So if the ground was an area of positive charge and this higher level was an area of negative charge, this negative charge would not want to go up there. So we would have to force it up there. That would be the job of the battery or the power supply. Now, once we get it up there, it has no problem wanting it. The forces will bring it naturally down against the direction of the field. So if it goes through, say, a light bulb, it will go through that from the higher to the lower potential, and in doing so, it will release energy in the form of joules, and that energy can be used to do just about anything we can think of. Make some light, make some heat, make a motor turn, like I said, etc. Okay, so again, applying this to specifically an electric circuit. We have the charge here, negative, and we have 2 points A or B. Now the electric field again points from positive to negative charges. So to take this electric charge that's negative in the direction of the electric field, to force it toward the negative, we have to do some work. So the answer is yes, we would have to apply some kind of force to make that happen. That means when we're done, the potential energy is going to be greatest at B, and that means this idea of an electric potential will be greatest at point B. Now if we're over here in this case, again the negative charge would be over here and the positive charge would be over here. If this was what we call like a D-cell battery, it would look something like this. This would be the flat side, and this would be the side that has the bump on it, and this would be your positive and that would be your negative. Now the electrons have no problem going from negative to positive. So this charge A, we don't have to do anything to make it go over there. It will go over there naturally. Since we don't have to do anything to it, it's like a ball falling. There will be no work done on it. Now it's no work done in terms of the energy that it loses will simply be converted into some other form. The potential energy will be greatest at A where it started, and then as it falls, think of it as falling, getting closer and closer toward the positive terminal, its electric potential would be less. Because of this idea that the charge is going to be analogous or similar to falling, we often talk about electric potential differences in terms of a drop when we go from negative to positive. Okay, so now this time we've got the negative charge and we've just changed the overall direction of the field itself, and it doesn't really matter. What matters is where's your negative, where's your positive. Now this is a negative charge. It is attracted to opposites, so it would prefer to stay here at point A and not go over to point B. So what's going to happen is we're going to have to do some work to take the electric charge from the positive, in this case it would be the positive terminal, say of a battery, to the negative terminal on the other side. And that's going to make the greatest potential where we go to, as we're heading toward a like part of the field, it's going to be a higher and higher potential. Once we get out to that negative terminal, the electron will then be able to go around the electric circuit because of what we gave, the energy we gave it inside the battery or power supply. And now in this case, the electron, the negative charge is next to other negative charge, and it's going to be repelled, so it's going to want to move down away from where it is without us doing anything. So we don't have to do any work. We start at our area of highest potential and we end up again close to what would be analogous or similar to the ground, and at the ground the potential energy and therefore the potential would be zero. So we're going to lose potential and we have less ability to do things in the future. Okay, so the big idea is, in general, when work is done on a charge to move from one location to another, potential energy increases when we do work, and therefore the electric potential increases. When a charge can naturally move from one location to another, then the potential energy will decrease, and therefore this thing we call the electric potential also decreases. So with our types of charge, if you talk about drawing the electric field, then this side of the field will be negative, this side of the field will be positive, and our negative charges will need to do work upon our negative charge if we try to take it toward the negative side of the field. On the other hand, if we have our negative charge and it's already near the negative side, it's not going to need us to do work. It's naturally going to want to flow or move toward the positive side. So when we set up an electric circuit, you're going to see the electric charge moving from negative to positive. As it does that, it's going to give up some of its energy and it's going to lose this idea of electric potential. Well, that's it for the big idea on this one. We'll start looking at in terms of circuits next to complete the rest of this particular concept.